So today we're going to talk about interval estimation. So point estimation, this is when we want to know the value of a population parameter, but all we have is a sample. All right, population parameters, things like the population mean, the population variance, those are the things we want to learn. We're going to use sample statistics to learn those things. So we're going to find the sample mean, the sample variance in order to get there. All right, since the sample statistic is a single number or a point on a line, it is known as a point estimate of the parameter. A sample statistic has noise to it. Remember from the end of last class, I was pulling samples from 150 observations, 27 at a time, and I was calculating means. Those means were varying each time. Right? Every time I pulled one, I was getting a different mean. All your sample statistics have a variance in and of themselves. They move around. Population parameters do not. Sample statistic, x bar, is the point estimate for mu, which is the population mean. The sample statistic p is the point estimate for pi, which is the population proportion. So this is when we're going to do confidence intervals. We actually have already done this in a way. All right, confidence interval is this thing right here, where we add mu, plus or minus, some level of confidence that we wanted to have, times its standard error. The only difference is that we constructed this with information we don't normally have. All right, we constructed this with a population mean that we don't know most of the time, and a population standard deviation that we don't know most of the time. So instead we're going to use the point estimates for those values. And we're going to call that interval estimation. So it provides more information than the point estimate alone. We know that the sample mean varies, so how much does it vary? We call this interval here the confidence interval. So think of it as, here is our point estimate, so this is x bar, here's our upper limit for x bar, and here's our lower limit for x bar. But unlike the interpretation we had in the previous chapter where I asked you, if I gave you the population mean, I gave you the population standard deviation, what is the likelihood that the sample mean would fall in between? We're going to reverse that. We're going to say, if I give you the sample mean, and I give you the sample standard deviation, what is the likelihood that the population mean will fall in between that interval? And I say that again to make sure we heard that. All we're doing is using the same tool from before, but understanding that we're using sample statistics in it. So we have to reverse the question. If I'm going to use the sample mean and the sample variance, what I'm really looking for is, what is the likelihood that the true population mean falls within that interval? Thus the name confidence interval. How much confidence do I have that the true population mean falls inside of that range? Given a population with a mu of 368 and a standard deviation of 15, if you take the sample size to be 25, we were able to calculate the interval before. Right now, all this works great when you know mu, which we never do. So what we're going to do instead is we're going to plug in x bar for mu. Everywhere we see mu, we're going to put in x bar. Everything else is going to work the same. It's the same exact setup as we had before, but instead of mu, we're putting in our sample mean. We're still using our z. Notice that now we're using a special notation with z. We're putting usually a probability in the corner. That's telling us how much probability it's covering in the cumulative sense. So 1.96 corresponds to having 95% of the data behind you. And then we have the standard error. Notice that the standard error also has special notation to differentiate it from just the standard deviation. But everything else is mechanically the same. Here's our 1.96. Here's our standard deviation of 15. Here we're taking the square root of the sample size, multiplying through. We get that entire thing. We call this entire thing here the margin of error. Margin of error that we're willing to accept. And then we add that and subtract that from the sample mean. So now what the confidence interval tells us is that if we were to do this 100 times, 95% of the time, the true population mean would fall within our confidence interval. So here are different confidence intervals. All these are different confidence intervals. Remember again that we're using x bar. And each time we go out and we pull x bar, it could be different. So here's a different x bar from this one and from this one. Okay? This is the true distribution, this blue line here. This is the true population mean. In some cases, the population mean does fall inside of the confidence interval. We did good. In some cases, it does not. So we have a mistake. We're willing to accept some mistakes. Now, this is an important lesson to learn right now. In statistics, there is a chance for error. Meaning, you can go out, you can do a study, you find something significant to be true, and it could have just all happened by pure chance. This is why repeating experiments is very important. Because you can get this result out here. You can go out, do everything right, everything by the book, and still get this result. And you're accepting that there's a chance that could happen. If it's 95%, you're saying that there's a 5% chance that you can make a mistake. So you're going to get studies that say GMOs cause autism. There's one that shows the expansions of Whole Foods and the expansions of autism. So does that mean Whole Foods causes autism? You can get those types of studies. And there's going to be many, many of them. I'll show you studies where coffee is good for you and coffee is bad for you, and then coffee is good for you again. I'll show you studies where wine's good for you, wine's bad for you, then wine with chocolate is good for you, but certain types of chocolate. It's because there is some error in them. So whenever you find a study, it's not enough to find it just that one time. They have to be able to repeat it. For a confidence interval, typically, you only take one sample of the size n. You only do this one time. You don't go out and do it 100 times. You typically don't know mu, and you do not know if the interval actually contains mu. That's the reality. You go out, you do a study, you don't know those first three things, and you'll never know those first three things. However, you do know that 95% of the intervals that you can come up with will contain mu. So if you were to do it 100 times, 95% of the time, you'd actually get it right. So based on just one sample, you can be 95% confident your interval will actually contain mu. And that's the idea behind the confidence interval. Yes?
So that 95%, that's going to be just given to us, right?
Well, you actually are going to select that.
Okay.
Right? So, unless I'm giving you a question, you're going to select that as a researcher. You're going to say, I want the interval to be 90%, or I want the interval to be even 99%. Right? You would then go out and find the appropriate z associated with that, and then construct the confidence interval. So here's the estimation process. First, you start off with a population that you do not know. Now, you want to learn something about this population. You go out and you grab a random sample from that population. Then you decide on how confident you want to be. So you go out and you say, I want to be 95% confident. You then grab a sample size that's sufficiently large in order for you to use the z-table. And then you go ahead and you construct your confidence interval around that. And so in just words, the confidence interval is your point estimate plus or minus your margin of error. Your point estimate here is going to be the sample mean, and your margin of error is going to be the standard error times your critical value. So the confidence level is the confidence that the interval will contain the unknown population parameter. We typically express that as a percentage, and we also write it as 1 minus alpha. Alpha is your level of confidence. Alpha is pretty standard across all books, so it is how much error you are willing to accept in the tails. So are you willing to accept 1% of error in the tails, 5% of error in the tails, 10% of error in the tails? There are going to be a couple worlds we're going to live in here. First, we can find confidence intervals for the population mean when we know sigma. That's the one we just did. When we don't know sigma, we got to find a new statistic. It's going to look really similar to what we just did, but it's not exactly the same. Now, this is the world we most likely live in, where we don't know the population mean and we don't know sigma. So when you know sigma, you're just going to use your z. You're going to assume normality. You use your sample mean. You do plus or minus the margin of error. With a known sigma, you can easily calculate your distance from the mean. You can separate it out so that you have the right level of confidence. So once we have our established level of alpha, or in other words, our level of confidence, we can go out to the z-table, we can get our critical values. The most commonly used critical values are those highlighted in purple. And those are what we call the standards for most statistical studies. And so for 90% confidence interval, z is typically equal to 1.645. For a 95% confidence interval, z is equal to 1.96. And for a 99% confidence interval z is equal to 2.58. You'll use those again and again and again. So if you need to memorize any z values, these are the ones you want to memorize. The rest you can find in the table. This shows the same process where once you have your level of alpha, you can determine how wide your margin of error will be. That margin of error, again, is trying to tell us what is the likelihood that the true mu will fall within that interval. So if this is true mu, you can draw a straight line down. Every single time we cross an interval, that means we were successful. Every single time we failed to cross an interval means that mu is not contained in there, or we're in the margin of error. So what this should tell you is that if you find a study that finds some weird result, it would still have to be replicated at least another 9 times in order for you to be really sure that's the true effect. Because it could be one of those 2 times, one of those 2 red lines. They just happen to be out in the tail. So here's one example, a sample of 11 circuits from a large normal population. Has a mean resistance of 2.02 ohms. We know from past testing that the population standard deviation is 0.35. Determine the 95% confidence interval for the true mean. So again, we set up our problem just as we've done before. We get our sample mean. Our sample mean here was 2.2. We want to know a 95% confidence interval. So from the previous slide, we know that's going to be equal to 1.96 right here. We know that the standard deviation is 0.35. So in order to calculate the standard error, we have to take the square root of the sample size, which was 11 circuits. And then we come back here, we find that our margin of error is 0.207, so that's the multiple of these 2 components. And then we just add and subtract that from the sample mean. Once we have that, we can say that we are 95% sure that the true population mean falls in between those 2 values. So 5% of the time, we're going to be wrong and that the true population mean actually falls outside of those values. So interpretation here. Although the true mean may or may not be in this interval, 95% of intervals formed in this manner will contain the true mean. The reason we're kind of harping on this is that you have to have the sense that this is being repeated over and over again. It just so happens that you're doing it once. In most cases, you would not go back and resample again. One, because it was really costly to get the first sample. But the idea here is that going back to the central limit theorem, you are repeating this process over and over again. Okay, so now we're going to move over to the case where we do not know sigma. So at this point, we don't know the mean. We don't know sigma. This is more like reality. Do you ever truly know the standard deviation? Probably not. In most real-world business situations, sigma is not known. If sigma is known, then mu is also known. Think about it. How do we calculate standard deviation? Square root of the variance, all right, so how do we calculate the variance? X minus mu. So in order to find the standard deviation, we would actually have to know mu. We actually have a new statistic we can use. It's similar to z, but it's not quite z. We're going to first replace our standard deviation with our sample standard deviation. That we can calculate, right? We just need the sample mean for that. We can find the sample mean, and we can calculate our sample standard deviation. And then we're going to use this thing called the t-distribution. It's actually called the student t-distribution. The student t-distribution allows us to approximate the z-distribution. In the past, this is what's been used for whenever they say you have a small sample. The reality is we only use the t-distribution. Now I'm saying that because in your book, it's going to say once you have sample size greater than what? 30, greater than 3.0, you have a large sample. So you can go ahead and use the z-distribution at that point. In reality, though, you never have a large sample. Now you're going to notice that it looks really similar to what we just saw. Here's x bar. Here is our level of significance, right? Our critical value. Here's that square root of n. And here is the sample standard deviation. So in words, it's actually the same. In words, it's still point estimate plus or minus the margin of error. In words, it's exactly the same. The only thing we've done is taken things that we don't typically get to observe and replace them with estimates of those things. So we don't typically get to observe mu, so we replaced it with x bar. We don't typically get to observe the population standard deviation, so we replaced it with the sample standard deviation. We don't typically get to observe whether or not a distribution is normal, so we're going to use something that takes that into account called the student t-statistic. Now the student t-statistic, the way that it adjusts for this lack of information is that we have to introduce this new value in there, which are called degrees of freedom. We've already seen this one time, this n minus 1. Where did we see this? Standard deviation or even the variance of the sample. Right? The reason we got that n minus 1 is that we had to eat up one of the observations in order to calculate the mean. Same thing is going on here. We're eating up an observation to calculate the mean. We're recognizing we're calculating the mean. What this does is that it reduces the sample size, if you will, that we're considering. So the degrees of freedom is the number of observations that are free to vary after the sample mean has been calculated. So suppose that the mean of three numbers is 8.0. Since the mean of these three values is 8.0, then x3 must be 9. Meaning that if you know two values, you know the third value. Right? If I tell you what the sample mean is, and I give you all but one value, you should be able to back out that last value. So that means that one value is not free. It can be completely determined once I give you the mean and those other values. Now this is how you should think about degrees of freedom. Here is the z distribution, that red line. All right, that's the one we just learned. The degrees of freedom adjust to how closely we match up with the z distribution. If our degrees of freedom are very, very large, it essentially says that we're almost matching the population again, which means we can go back to assuming a normal distribution. However, if our degrees of freedom are low, this pushes down the whole distribution. What happens to the tails once we push it down? The tails get bigger, right? So we're allowing for more error into those tails. And we're allowing for more space to go into those tails. Which means that when we construct our confidence intervals using a t distribution rather than a z distribution, are they going to get wider or are they going to get narrower?
Wider.
Wider. They're going to get wider. Because now we have to go further into the tail in order to get 95% confidence. Alright? So the t distribution takes into account that we're using sample statistics, which have an error to them. And it does that by adjusting the confidence interval. It does that by making the confidence intervals wider. Alright. Now the other adjustment you have to make with the student t distribution is that it doesn't have the same table as the z table. In the z table, inside of the table you had probabilities, right? And along the top and across the top and down the first column, you had z values, right? This does it backwards. You have the t values inside of the table, and you have the probabilities going across the top. So let me show you what you would typically use. Here you have a student t table. Down the first column, you have your degrees of freedom, which means you'd have to find your sample size, subtract off 1, and then go to that row. If I told you that our sample size was 16, you'd go to the row of 15. The next thing you have to do is ask yourself, well, what level of confidence do you want? What is your alpha going to be equal to? So far, we've only been talking about two-tailed, meaning that, I erased it, but the two tails of the distribution. So we're going to concentrate on this top row right now. If I want there to be 10% in both tails, I would go to this column here. Right. So alpha here would be 0.10. And then it comes down to 15. So now I'm going to have a t value of 1.753. Go back to your notes and tell me what is the Z value for that same thing. So in other words, what is the Z value such that I have 10% in either tail? Sorry, 10% altogether. What is the Z value for a 90% confidence interval?
1.65.
1.645. 1.645. About 4 slides ago. When I showed you the values. And here we're at 1.753. So even if we had the same standard error, we already have a wider confidence interval. Alright, so we got same mean, same standard error. In fact, we're using a student t statistic. With that sample size, our confidence interval got wider. So the way you would read these tables is that you would find your degrees of freedom, you'd then find your level of significance, and then you'd ask yourself, are you looking at just one tail or two tails? If you're looking at just one tail, then you go back across the top, use it the same way. So if you want 10% up in that top part of the tail, and we come down here to 15, it would be 1.341, which was similar to what you found with Z, right? So you can see here what happens to the level of the t statistic as the degrees of freedom increase. As the degrees of freedom increase, we approach the Z value. And all we're doing there is the same thing with the standard error. As your sample size gets larger and larger, you're approaching the population, so it's becoming more normal. We can see that going across all the values. You see those primary values of a 99% confidence interval, a 95% confidence interval, and a 90% confidence interval. Those are those three main values. It said if you had to memorize 3 values in the whole Z table, these would be them. So then we want to construct our confidence interval for the sample mean, given an unknown standard deviation. We would just construct the same way we have so far. We take a random sample of 25 observations, X bar, say, is equal to 50, and the sample standard deviation is equal to 8. We want to construct a 95% confidence interval. What we do is we find our degrees of freedom, it's going to be equal to 24. We then have to go to our table. We go down to row 24. We want it to be 95%, so if we look at 0.025, we're using the top column, or if we're using the bottom column, it's 0.05. And we pull it off from that table to show you that it's consistent. Here is 24, and here is our 0.2064 that we just found. And then we just plug it in. Alright, now we do the same thing over on the population proportion side. So all this is going to be a rerun. Just we're going to be replacing X bar with P. For the population proportion, if we know P, then we're set, right? In this case, you don't need to know mu per se, right? If you know P, you already have everything you need in order to calculate both the mean and the standard deviation. So interval estimate for pi can be obtained from the sample proportion P, but must add an allowance for uncertainty. We will estimate this using the sample data. So the standard deviation now becomes P times 1 minus P divided by N, and we take the square root of that. This isn't new from last chapter. That's exactly what we used for last chapter. The upper and lower confidence limits for the population are calculated with the formula of P plus or minus Z. Note again here that if we have a large enough sample and we can use population proportion, we can approximate it with a normal distribution. And then just like we did before, we find the critical value for Z. We multiply it times the standard error. That gives us the margin of error. We plus or minus that from the the sample proportion. Notice the steps are the same. Point estimate, plus or minus, margin of error. Exactly the same. Point estimate, plus or minus, margin of error. So when you're doing these problems, first thing you do is find the point estimate. Here you calculate the standard error. Three, determine the confidence level. Find the critical value associated with that confidence level. And then just plug and chug. Again, the interpretation is the same, that we're repeating this process over and over again. We are 95% confident that the true percentage of left-handers in the population is between 16.5 and 33.49, although the interval from 0.1651 and 0.3349 may or may not contain the true population. 95% of all intervals formed from samples of size 100 will contain the true population. Sample size. So how big does my sample size need to be? Again, I will repeat my mantra, as big as you can possibly get it. But if you need to determine the minimum level that you had to have in order to have a certain level of margin of error, this is how you'd go about doing it. Remember, the margin of error is that second part, right? This entire thing is your margin of error. So, the required sample size can be found using the following formula. You need margin of error and you need a level of alpha. Once you have those two things, you can then construct the number of observations you would have to have. So again, this thing back here is our margin of error. This whole thing back here is our margin of error. N sits in there, right? N sits inside of our margin of error. So, if we can pick a number for E, if we want E to be 2, for example, right? You have to choose it here. You have to choose what E has to be. Then we can back out what N should be. So all we're going to do is solve this for N. This determines the smallest sample size that I can have so I meet that error. This is mainly used in clinical trials when you want to know how big your how big your sample needs to be in order to justify whether or not you can find a result. You might be concerned that bringing in too many people into a clinical trial could be unethical. So you're trying to find an equal balance between having a sufficiently large enough sample size to test the drug and also not too large so that you could possibly be doing harm to a lot of people if the drug is bad. Alright, so to determine the sample size for the mean, you must know three things: the desired level of confidence, the acceptable sampling error, and the standard deviation. As long as you have those three things, you're good. So here's one example. If sigma is equal to 45, what sample size is needed so that the estimated mean is plus or minus 5 with a 90% confidence interval? So we're saying here that E is equal to 5. All right, E is equal to 5. If we want a 90% confidence interval, that means we have to go out and get the critical value for 90%, which hopefully we know by now is 1.645. Square that thing. We square it times the standard deviation, so it essentially becomes the variance again, and we divide that by 25. So for this particular example, we would need a sample size of 220. Why should we always round up?
If you're doing a clinical trial, it would be hard to find one person.
Yeah. Right? You either have the observation or you don't. Now, if sigma is unknown, it can still be estimated, same way we did before. I mean, we go out, we get a sample variance, we use that sample variance and get the sample standard deviation and do the whole process all over again. We can also replace the z with a t and do it again. So if we want a conservative value for our sample size, we can do that as well. Which again, in reality, is what you would really do. Because you wouldn't have a z, you wouldn't have a population standard deviation. That's what you'd need to do. We can do the same thing for the proportion. So for the proportion, you can go back out, you can get your sampling error, you can multiply it times z squared divided by the error squared. This is the same process, it's just that now this becomes our standard error. But we solve it the same way. So instead of having a sigma squared somewhere running around there, we're going to have this pi times 1 minus pi. Now the reason I'm pointing this out to you is I don't want you to memorize every single little type of formula when they are essentially the same. The intuition is the same for both of these cases, except you're replacing one, so sample mean, with population proportion. But the intuition is the same. So So therefore, to determine the population proportion, you need three things. Again, the desired level of confidence, the acceptable sampling error, and the true proportion. Since you don't have the true proportion, you're going to replace it with what? Just as this with the mean. If you don't have mu, you replace it with what? X bar. So if you don't have pi, you replace it with what? P. In this case, we need a sample size of 451. Alright, some ethical issues. When reporting a point estimate, you should always include a confidence interval estimate in order to reflect sampling error. If you don't do that, it's very easy to lead people astray. So for example, you're going to see a couple of polls coming up in the near future, right? We have an election coming up. And you're going to hear that one candidate is beating another candidate by, say, 5%. That sounds like a lot. Sounds like this is over. What if the confidence interval associated with that 5% crosses 0? Right? Meaning it goes, say, from -2 all the way up to 8. That means they could either really be killing them, if they're over there on the 8 side, or they could be in a dead heat. Or I could tell you a different piece of information. What if it's just plus or minus 1%? Now you know. Right? You know there's a 95% chance that if everything stays the same, this person is going to win. Because they have a significant gap over the other person. Yet in both cases, I just told you that the person was winning by 5%. And those are two totally different scenarios. 2, you want to report the level of confidence, just so they know how wide this interval is. If that interval seems to be very narrow, and yet you're still reporting the 99% confidence interval, that's saying a lot, right? That's saying that your estimates are very tight. But if you're only reporting the 60% confidence interval, there's a reason your confidence interval is very tight. And you're still leaving 40% of the chance. Next thing is you want to report the sample size. This is a killer for a lot of small clinical trials. You hear this study, the study comes out, it sounds great, then you find out 4 people were involved. Lastly, you provide interpretation of the confidence interval estimate. One of the key things that people who deal with statistics do is that they have to take these numbers and translate it in a way that a layperson can understand. That is what you actually get paid for. Alright, and that's really it. That's how you move from being stuck in the basement with a computer to the corner office. Because you have to go out and tell people for the board of directors or for your investors and explain to them what you found. And if you tell them, oh, well, my X bar is plus or minus my margin of error, they go, no, find the other guy. Alright? That didn't tell them anything. You have to be able to translate that into real words.